All right, so are you in review mode?
Yeah.
No new material?
Yeah, we just started working on, what's this? Non-linear inequalities.
Okay.
And I think I have a couple questions on my homework.
All right.
Actually, no, I don't. That was pretty easy for me, but it's the stuff before that.
Solve this for me.
So you would bring the 4 over to the other side, and then it would be difference of squares, so x minus 2, x plus 2, and then those would be your was it like conjugate numbers or something?
Critical points.
Yeah. And then you put those on a number line.
Okay.
Then just test.
Okay. So you know how to do those. Okay.
Yeah.
The other way that's a little easier to do this specific one is take the square root of both sides, but instead of it being x equals plus or minus 2, it's x is greater than the plus, and if it were minus, then you would have to change the sign because we've divided by a negative. So you can do it kind of directly like that. And that helps actually a lot when you're taking inequalities with a square root or with a nonlinear.
Yeah.
As long as they're quadratics.
And before that, we were working on, try to find my notes. Working on zeros of polynomial functions.
Okay. You have some?
Wait, maybe it's, no, it was that, it's where you find the horizontal and vertical asymptotes.
Okay. Do you have some of those?
Yeah, okay. So it's just,
usually they'll give you a function and ask you for the vertical and horizontal asymptotes.
Yeah, this one asks for the horizontal asymptotes, the vertical asymptotes, the x and y intercept, and to graph it.
Okay.
And it is x squared over x squared plus 9.
Okay. Let's talk about the vertical asymptotes.
Those come from the denominator, right?
Whatever the denominator makes the denominator 0.
Doesn't nothing make the denominator 0?
None.
Oh, okay, because I was trying to solve it and I did like...
Nothing but imaginary numbers make the denominator 0, and we're always in the realm of real numbers when we're talking about vertical and horizontal asymptotes.
Oh, so it's... Okay.
Let's talk about horizontal asymptotes. Those are usually a little harder. There's 3 different cases. There is if the power of the variable is greater in the denominator than it is the numerator, like 1 over x, then your horizontal asymptote is always y equals 0. Yeah. And that would be true even if it was x over x squared plus 1, because this is bigger than that. Y is equal to 0 is your horizontal asymptote. So that's one situation. Second situation is where the exponent of the highest degree is the same, which is the case in this problem, then your horizontal asymptote is y equals the ratio of their coefficients. So if I had something like this, what's the horizontal asymptote going to be?
It'd be 1/3.
Y equals 1/3. Remember, we're defining the equation of a line. Okay. All right. And then the third situation is where the power in the numerator is 1 more than the power in the denominator. And what you do here is do the division by longhand. You know how to divide a polynomial by another polynomial?
Yes.
And whatever the quotient is your oblique asymptote. In other words, you don't just have vertical and horizontal asymptotes. There also are oblique asymptotes, where the function, does something like that. It's asymptotic to that oblique asymptote. And whenever you have the numerator exactly 1 degree higher than the denominator, like this, the quotient is the equation of that oblique asymptote. You have some remainder, but you can ignore the remainder. The important part is the definition of that oblique asymptote. And it turns out to be linear. It's going to be a straight line. As long as the power of the numerator is 1 greater than the power of the denominator. In other words, that division is going to result in some linear function like x plus 2 with some remainder. Okay? And the x plus 2 is the equation of the oblique asymptote. So, I don't know if you've talked about oblique asymptotes or not in class. But that's the 3 different types, or the 3 different methods of figuring out horizontal asymptote. What was the other thing besides vertical and horizontal asymptote? The x and y intercepts?
Yeah.
Okay, let's talk about the easier thing, which is the y-intercept. What is true at the y-intercept about x?
X is 0.
Okay, so what is the y-intercept for this?
It's just 0, because if you plug in 0 for x.
The harder one is the x-intercept. To solve that, we need to make y equal to 0, because that's the definition of x-intercept, is it's where y is equal to 0. Now, when you have 0 equal a fraction, it only can be true if this numerator is equal to 0. So the x-intercept has to be what?
0.
And what was the last thing they asked for?
To graph it.
Okay. Well, we start, there's no vertical asymptotes. There's a horizontal asymptote. There's an x-intercept right there. Oops. And a y-intercept. Now, when they say graph it, are they allowing you to use your calculator, or is this graph without a calculator?
This is without a calculator.
Without a calculator? Okay. So, you'll notice that, well, let's see. We know we're going to be asymptotic to that horizontal asymptote. We know that it goes through here, and we know that as x goes to infinity, we can see that this thing's going to go to 1. So it's going to look something like that, approaching the line y equals 1. And then as x goes negative, this ratio is still positive, and the closer that x gets to negative infinity, the closer that ratio gets to 1.
Yeah.
So that's its graph right there. Maybe not exactly the way your grapher would show it, but close to that.
Mm-hmm.
And notice that y can never be negative, because there's no way the numerator can ever be negative, and there's no way the denominator can ever be negative. So y is always positive.
All right.
All right.
Okay, this one it's asks you to do the same thing.
Okay.
And it's 2x squared minus 5x minus 3 over x cubed minus 2x squared minus x plus 2.
Okay. And do they ask you about holes?
Yes.
Okay. So additional to vertical and horizontal asymptote, they want to know about holes. Now, holes occur where you can factor something out of the numerator and the denominator.
Mm-hmm.
So our first task is to factor each. Well, let's start with the numerator.
Mm-hmm.
I know that much. What else?
It's
What do I know about the signs?
I think it's both going to be
They have to be opposite. The only way I can get a negative 3 is with opposite signs. Now, that either means plus minus or minus plus. Now, I have to allow for either one because the coefficient on the x term is different. It's 2 and 1. So this becomes a much harder factoring problem. But there aren't that many factors of 3 for me to try, so let me just start from the get-go of trying 3 and 1. Does that work? No. In other words, 3x minus 2x does not equal minus 5x. So let me try 1 and 3. That's pretty much the way I do this, is by just trial and error. Does that work?
no.
Well, the way I tell if it works is I do my two smiley faces. This one is plus x. This one is minus 6x. Add them together, you get the middle term. That's what we're looking for.
Mm-hmm.
So that works. So that's the numerator factored. Now, the denominator is a little harder to factor. First of all, it's a cubic, but it's a cubic that lends itself to grouping.
Mm-hmm.
You know what grouping is?
Yeah.
Okay. So I'm going to group these two terms, and I'm going to group these two terms. And notice when I group the second set of terms, I have to turn that plus 2 into a minus 2 because I added parentheses.
Mm-hmm.
You see that? I haven't changed it.
Yeah.
Now, on the front end, I factor out an x squared, leaving x minus 2. On the back end, I have the x minus 2. And how does this factor?
So it's going to be x plus 1, x minus 1, then x minus 2.
Yeah, the first step, let's do it one step at a time. What we're doing here is a little unusual. We're factoring out a binomial.
Mm-hmm.
Okay, and when I factor out that binomial, it leaves behind x squared minus 1. And then the x squared minus 1 factors into x minus 1 and x plus 1. So that's how I get those three factors.
Mm-hmm.
Okay, so now let's rewrite this denominator as these three factors. Wow, I'm shocked that none of them was the same. Because it's only if one of these is the same that I can cancel it out and it creates a hole.
Mm-hmm.
If I don't cancel it out, there's no holes. So it's a straightforward equation. What are the vertical asymptotes?
2, 1, and negative 1.
Okay, vertical asymptotes are lines, so it's x equal 2, x equal 1, and x equal negative 1. What are the horizontal asymptotes? And the easiest way to figure those out is to go back and look at the master equation.
Mm-hmm.
So based on the highest degree polynomial in the top and the bottom, what is the horizontal asymptote?
Y equals 0.
Okay. So we're going to draw our three vertical asymptotes and our horizontal asymptote. Most of these functions are generally hyperbolic in nature. In other words, we know they're going to look like some variation of 1 over x. Notice that that converts to 2 over x. So that means we're going to have a function that looks basically like this, only with more vertical asymptotes. We have 3 vertical asymptotes. So what else do they want to know about this? They want to know x and y intercepts?
Yeah.
What are the y-intercept?
Y-intercept would be negative 3 halves.
Yes. And the x-intercepts are a little harder. In other words, we want to set that equal to 0.
Mm-hmm.
So what are the x-intercepts?
Negative 1 half and 3.
Okay. So let's see. Negative 1 half is right there. 3 is right there. Excuse me. My pen is acting up. Huh. Ah, there it was. The y-intercept is minus 3 halves, so we know the curve needs to go through all of those points, and it needs to be asymptotic with each of those vertical asymptotes.
Mm-hmm.
What else besides x and y intercepts? Other than graph, is that it?
Yeah, that's it.
Okay. Well, one of the key things we need to know in order to graph it is whether we start here or whether we start there.
Mm-hmm.
Once we know how to start, we'll know how to move right to left. So how do I know whether I'm in this quadrant or this quadrant? What test can I do?
You can just do 4.
Okay. And 4 gives us 9 times 1 over 2 times 3 times 4. That's a positive number.
Mm-hmm.
So the fact that that's a positive number tells me I'm in that quadrant.
Yeah.
So I know that much. Now, usually on these functions, hold on a second. Notice that I didn't go through the x-intercept, and I need to.
Okay.
And you can cross horizontal intercepts.
Mm-hmm.
What you can never cross are vertical intercepts. You can cross horizontal intercepts and you can cross oblique intercepts. You just can't cross vertical intercepts, ever. So, just to skip the middle part for the moment, let's figure out what's happening over here.
So you just test -2.
Okay? So that's negative, that's negative, that's negative, negative, negative. So I got 2 negatives divided by 3 negatives. Negative puts that like that. So that's my essence of the hyperbola. Now the only thing I need to do is figure out what's going on in between. Well, I know that it crosses here, and usually with these kind of functions, if you're going up to positive infinity, you come down from negative infinity.
Mm-hmm.
So you do something like that, and then we're going to do something like this, and it tells me I'm going to cross the x-axis there. Didn't do what I wanted it to do.
I'm sure go the other way.
Well, the thing is, I want to come up from negative infinity because I went from positive infinity. So I'm trying to do that the whole way. Let me plot this real quick on Wolfram Alpha, see what it looks like, and see what I'm doing wrong here. Have we used before? Wolfram Alpha?
No, I never have.
No, we haven't used it. It's pretty nifty. If you don't have it, it's worth putting on your computer and using.
Is it like an app?
No, it's like a super duper calculator. The biggest thing, I'll show you what it does here. 2x squared, what is that, minus 5x?
Mm-hmm.
Minus 3 quantity divided by x cubed minus 2x squared minus x plus 2. Now the beauty of Wolfram Alpha that your calculator doesn't do is it gives you the feedback. In other words, it's real easy to make a mistake when you input a function into your calculator. Well, this tells you exactly what you entered. And that's what I was trying to enter. Okay? So now it's going to show the graph. All right. How does that compare to? And it shows it in 2 different scales. Notice the mistake I made was in that right-hand side. I tested a number and saw positive, so I immediately thought that it was in that upper right-hand quadrant. Well, it really wasn't. It was in the lower right-hand quadrant. But since it went through the 0, part of it was in the upper right-hand quadrant. Notice that I have the reflection of that in mind. And the real graph goes from down across the back. And that changes everything, because now I'm going to end up being correct on the middle and ending. In other words, notice the part that goes between the asymptotes 1 and 2 is this part here on Wolfram Alpha. And then the part that goes between the asymptotes minus 1 and 1 is this part, the opposite of mine, which figures because I've got the first part and the next 2 opposite, and that's why I ended up not coming out right on the 4th part. The fourth part I got right. That part there.
Yeah. So for every like section in between vertical asymptotes, do you have to have a graph of some sort?
Yeah, the only question is to whether it crosses the x-axis or not.
Mm-hmm.
In other words, this was like this. The middle part was here, and the part to the right was like that.
Yeah.
So yeah, notice that I end at negative infinity, so I come down from positive infinity. I don't have any x-intercept there, so I know it has to turn around and go back up.
Mm-hmm.
I end at plus infinity, so the next one has to start at minus infinity.
Mm-hmm.
I do have an x-intercept there, so I cross it. So it goes from minus infinity, right there, excuse me, all the way up to positive infinity. And then on the other side of the asymptote, I come up from negative infinity.
Yeah.
And that's basically how you graph this. Now, in all honesty, this is the toughest one I've ever seen. Normally, they give you 2 vertical asymptotes at most, not 3. When there's 3 vertical asymptotes on a hyperbolic type function, you do it exactly the way we just did it.
Okay.
Only if I'd have spent a little more time testing more points, I would have figured out that my first quadrant was wrong.
Mm-hmm.
And then I would have been fine throughout the whole thing. All right.
So should we just review some past, like from the start of chapter?
Whatever you like, Griffin. You're the one that's kind of in charge here. Whatever you feel the need to review the most. Now, are you just having quizzes, or is this your semester final? Your semester final isn't until next week, probably, right?
Yeah, it's next week.
All right.
And he's going to give us like a review packet, so.
Good.
Let's see. Let's be good on this. All right, here's one. Page. All right, so this says find all the zeros of the polynomial function, determine the multiplicity of each zero, and graph the function.
Okay.
Using a graphing utility.
Okay.
So it is t to the 5th.
T, as in Tom?
Yeah, you can just do x though. I don't think it matters.
It doesn't. In fact, I prefer X because it doesn't get confused with a plus sign.
Yeah. T to the 5th minus 6t cubed plus 9x.
That's it?
Yeah.
Okay, what's
Find
the
all
first?
the-
What's the first thing we can do?
we can factor out an x.
How do we handle this quartic right there?
Then you pretty much just pretend like the x to the 4th is an x squared.
Yeah, we use a method really called substitution, where I'm going to let u equal x squared, whatever this term right here is. In other words, this is what I call a quadratic in disguise, which means that this term is the square of this term. It doesn't always have to be x and x squared. It just has to be this term is the square of this term and a constant, and we can use this substitution method to rewrite it. In other words, it now becomes that's factorable easily. It's a quadratic. Now we go back in and we resubstitute. For u, we put back in x squared. Now what's the next step?
Do you just find the zeros?
Okay. What are they?
0, plus and minus root 3, and then another plus and minus root 3.
So the multiplicity on this is what? And the multiplicity on this is what?
The 0 is 1, and the 3 is 2.
Okay.
So when you graph that at both plus and minus root 3, it's going to bounce.
Yes. When you have even multiplicity, it kisses the x-axis and doesn't cross it.
Mm-hmm.
When you have odd multiplicity, it crosses it. So we know the curve's going to cross there. Excuse me. It's going to cross there. It's going to bounce there and there. So really the only thing left to figure out here is, well, it'd be nice to know a y-intercept. What's the y-intercept? Huh?
Isn't the y-intercept just 0 also? Because that's 0, 0.
Yeah. So, okay. So the only thing we don't know is the end behavior.
Mm-hmm.
In other words, we don't know if it starts from the lower left or the upper right. It's pretty easy to figure out that it's going to look something like this. Or a variation of that. Notice that I have a bounce at those 2 points. I have a crossing at that point there. It's a 5th degree polynomial, so I should have 4 relative mins and maxes. So this fits all of that definition. The only thing is that I don't know whether it comes from the upper left or the lower right. So before I do that, let's figure out the end behavior. You're familiar with that?
Yeah.
On the left-hand side, as x goes to negative infinity, where does y come from?
Negative infinity.
Okay, that means that I'm going to start down here. And by the same reasoning, I know the right-hand end behavior is going up to positive infinity.
Mm-hmm.
So this thing must do this. Kisses there. It's got to go back down. It crosses there. It kisses there. It's got to go back up. Must look like that. There's no y-intercept other than y equals 0. We've got 2 bounces. That should be it.
All right.
If you like, I can plug that into Wolfram Alpha and we can confirm it.
Okay.
It's not too hard to do. Read it to me again. What is it? X to the what?
It is x to the 5th minus 6x to the 3rd, or 6x cubed, plus 9x. Okay. I'm pretty good with dividing.
Synthetic division?
Yeah.
Okay. If you had to do the rational factor theorem, the P over Q? For finding zeros of like cubics and quartics?
I don't think so.
Well, I don't want to get into it if you haven't done it, but the problem you gave me earlier was a variation of something like this. If it was this and I said find the zeros of that without a calculator, that's a huge problem. You have about 5 possibilities, or actually 10 possibilities, and you have to try each one. Dividing it is a very tedious, time-consuming. It's called the rational factor theorem. It's usually referred to P over Q, where P is a factor of the constant and Q is a factor of the coefficient of the highest polynomial term.
Yeah, we actually did do that.
Okay. I thought probably you had, given what you were talking about elsewise. So, like I said, you're not going to get more than one of these on a test because they're just too time-consuming. Notice that this does not lend itself to grouping. The ratio of this coefficient to this coefficient is not the same as the ratio of that coefficient to that coefficient. It was the only reason we were able to do grouping on the other one, was because it was set up perfectly to do grouping. In reality, most cubics can't be factored so easily.
Our teacher lets us use a calculator to find what
the zeros? Okay, so you know how to do that? In other words, you're not ever going to be forced to find these manually?
No.
Or to find the possible rational factors?
I think we find the possible rational factors by using a calculator.
Okay. Well, the calculator would tell you the real zeros. It would give you all the zeros. It wouldn't give you the possible rational factors. But maybe you haven't gotten that far. I don't really want to go there if you haven't. So that's fine. We'll leave it at, you can put that into your calculator, and as long as you know how to find the zeros. You have a TI-84 or the Inspire CI?
Get the TI-84.
Okay. The other beauty of Wolfram Alpha is it gives you your zeros. Notice that it not only graphs it, but it gives me the 3 roots right there. Without having to do that silly trace. That TI-84 is really kind of archaic in the way it forces you to come up with mins, maxes, zeros, intersections, all of that. I think, at least. I mean, compared to the technology that's out there.
Yeah. Okay. Let's see what else. So could we do a problem where it, like we were doing before, where it would have a hole in the graph?
Yeah.
Not really.
Let's take this function here.
Okay.
This is actually the classic one that is the textbook definition. From this, you know that x cannot be minus 1. But once we factor the numerator and we cross that off, now it looks like that turns into this function. And there doesn't appear to be any such restriction on that. But there is. The original restriction always carries forth no matter how you factor it or anything else. So if I'm going to say x can't be equal to minus 1 from the get-go, then I have to apply it here also. X cannot be equal to minus 1. So when I go to graph that, it's going to look exactly like x minus 1, which is that line right there.
Mm-hmm.
But it still has the restriction on it that x can't be equal to minus 1, so I have a hole right there at minus 1. Now, if you were to graph this in your calculator, the original function, you would not see that hole. The reason being is that it's microscopic. It is 1 point on a number line. It's, you know what I'm saying?
Yeah.
So there's no way that hole would show up on your calculator or in my Wolfram Alpha if I typed it in there. But we know it's there. Holes always carry forth no matter how many times you factor something out. And so if you were going to manually graph it, this is the proper way to graph it, is to show the hole. And you're going to get a hole wherever you would have normally gotten a vertical asymptote. Notice that if I don't notice that this will factor, I'm going to tell you right off the get-go there's a vertical asymptote at x equal minus 1, which is not true. There isn't one.
Mm-hmm.
It turns into a hole because it cancels with the factor in the numerator.
Yeah. So could we do x plus 1 over x squared minus 1? Because wouldn't that change it kind of a lot?
Yeah. First of all, what's the domain on that?
The domain would be...
What can x not be?
X can't be...
Can't be plus or minus 1.
Oh, yeah.
Okay? So that domain has to apply throughout. So even though I factor that, you know how I factored it down to that.
Uh-huh.
And this has a asymptote at x equal 1, but it still has this hole at x equal minus 1.
Mm-hmm.
So if I'm going to graph this thing, I've got the vertical asymptote here. I've got a horizontal asymptote there. I know that when that part plots, it's hyperbolic in nature. And so this part's going to look just like this, except there's going to be a hole right there at minus 1.
Mm-hmm.
There's going to be a hole where there would have been a vertical asymptote.
Okay. Okay, I see. Okay. Anything else?
Now sometimes you'll get a problem. Let's say we get a function. And we know there's two vertical asymptotes, and we know there's a horizontal asymptote.
Mm-hmm.
And now the question is how to graph it. And they don't tell us much. And our choices usually are going to be, well, it usually starts up there, and it comes out. We don't know if it's which side it comes out here. But in the middle is where it's always interesting.
Yeah.
We know it comes up from there, but in order to know whether it crosses the x-axis or not, we have to decide, are there any x-intercepts?
Mm-hmm.
So if you try to solve for the x-intercepts and you cannot solve it, it means no, there aren't, which means this thing has to turn around and come back down. If you try to solve it for x-intercepts and you find an x-intercept, say right there, then that means it's going to keep on going and come out up there.
Okay.
And then probably it looks like that. So you have to determine whether or not it has an x-intercept, and sometimes you have to determine whether or not it can cross the horizontal asymptote. And you do that by setting y equal to that horizontal asymptote. Say the horizontal asymptote is y equal 1. Well, you substitute 1 for y and you try to solve the equation. And if you can solve it, it means it crosses it. If you can't, it doesn't. I mean, those are kind of general things, but you have any last specific problems you want to cover? Griffin, you still there? Griffin? Griffin, are you back?
Oh, yeah, there we go.
Yeah, I lost you for a moment, and I noticed my GoToMeeting said you were offline.
Yeah.
Okay, did you have any other problems you wanted to cover before we wrap it up?
Not really. Definitely
Sure.
never.
Okay.
Yeah.
You're going to have like a quiz between now and your final?
Yeah.
All right. That seems to be what most people are doing, is taking quizzes this week, and then all of next week we'll be reviewing for finals.
Mm-hmm.
Just a word of warning is you might want to, if you want to schedule something, do it soon. The next 10 days are the busiest 10 days of my year.
All right.
Okay?
Okay.
All right, Griffin. Talk to you next time.
Yep. Thank you.
Bye-bye.